Hello, everybody. Today we are dealing with one interesting topic of the GMAT quantitative section, which is called counting methods. Here we deal with problems of combinatorics, permutations, combinations, etc. Let's begin. Most of these problems are based on a principle that is called the multiplication and addition principle. It's all about the following situation. If you are asked to count the number of ways in which two different events can happen together, you have to consider the number of manners in which each one of them can happen, and then you have to ask yourself if the two events are happening at the same time or together, or if they are happening in an alternative way, right? In which case, you have to decide for the operation of multiplication or the addition of the number of ways in which each event can happen. If they are supposed to happen together, you should multiply the number of ways in which the two events happen. But if you just need to figure out how they can happen alternatively, then you just need to sum the number of different ways for each event. Okay, so let's see several cases that are commonplace in the GMAT. The first case is what we call rearrangement or reordering of all elements. In this general method, we're going to draw spaces for each value we want to rearrange. Next, we're placing a value for each space that represents the number of options you have to count those individual spaces. And finally, you multiply all the different number of options. For example, in how many ways can you arrange the letters A, B, C, and D? We place 4 spaces, as you can see here, and in each of them, we place the number of options that we have for each letter. In this way, for the first letter of this arrangement of 4 letters, I can pick, okay, the letter in 4 different manners, because we have 4 different letters. After I have chosen the first letter, then I have 3 remaining letters from which I can pick the second letter. After I have chosen a second element, I have 2 elements left over, so that I can pick the third element in 2 different manners. And after I have already used 3 elements of these 4 and placed them in the first 3 positions of this arrangement, then what I have left is just the last element. So I have just one option for the 4th position. The product of these options is what we call 4 factorial, okay? And this represents the total number of manners, which is actually 24, in which the 4 letters can be rearranged, okay? So in general, for number n of different elements or symbols, you can rearrange all of them in n factorial ways. What happens when you have an arrangement with repeating elements? Well, if you have an arrangement with repeating elements, then first you can understand that if you have, for example, these 8 elements, symbols, the 8 letters, 2 A's, 2 B's, 3 C's, and 1 D, yeah, just doing 8 factorial will count the cases in which you can interchange or rearrange all the 8 letters. But this also includes those cases in which you interchange the A's or the B's or the letters alike, among one another. So those special cases don't constitute a new arrangement because they read the same, right? For example, in any given arrangement, for example, this, you can swap the position of the 2 A's, but this would generate just the same arrangement. So, in order to remove the repetitions, we can consider that for every possible position, in the case of the 2 double or the 2 duplicate A's, actually all the arrangements within 8 factorial are doubled. And each of them, can be with the a's in this order or with the a's in this order. For any given position, you have double the valid arrangements. So in order to remove, you divide by the factorial of 2, which is the number of manners in which the two a's can permutate. So we first divide by 2 factorial. But after doing that, we also realize that the two b's can swap, their position in any given arrangement. So there's also a duplication of all the arrangements because of the possibility that the b's can exchange positions for one another. So we also divide by 2 factorial again in order to remove the repetitions due to the repeated b's. With the c's, we could reason likewise. The c's can, change positions for one another in totally 3 factorial ways. That is 6 possible ways. So when I divide by 3 factorial, I'm removing those duplicated or repeated arrangements that are due just to moving the c's among themselves. The letter D is different because every time I move the D in a different position, it actually generates a new valid arrangement. So dividing by 1 factorial actually does no harm because it simply doesn't change the number of arrangements. So you can, from here, basically deduce this formula for the number of arrangements with repeating elements, which would be the total number of elements factorial divided by the factorials of the individual repetitions of each element. Okay, how do you operate this? Well, in this case, what you can do is expand the factorial in the numerator so that it appears the greatest factorial in the denominator. In this case, 3 factorial, because 3 factorial just represents 3 times 2 times 1. So once you expand up to the biggest factorial in the denominator, you just cancel first that factorial and then the others, which are usually smaller, right? So for example, here 2 factorial times 2 factorial is just 2 times 2, which can cancel with 4. So you have just the product of these 4 factors, which is 1680. Okay, so let's now check a simple example. In how many ways can you rearrange the letters of the word casa, right? Stands for, it's the Spanish for house. So it would be 4 factorial after the 4 letters, 4 symbols, divided by the repetitions, if any, which is just here, these 2 repeated, 2 factorial, and the C is just 1 time, and the S is just 1 time. So the, 1 factorial division means nothing, right? So it's 4 factorial, 4 times 3 times 2 factorial divided by 2 factorial, it's 12, the answer, okay? For an exercise, you can try and do this. In how many ways can the 11 letters of the word Mississippi be arranged? All right, so you can try this as an exercise. Let's see the case 2. It's codes. Here, there are 2 main characteristics, okay? For codes problems, they may give you, for example, a number of symbols, such as the letters A, B, C, D. They can ask you, okay, you can make codes of 4 letters with these symbols, and the elements may be repeated, or they must be different digits. Okay, the problem must clarify that. If it doesn't, then you can assume that the elements may be repeated. You can always assume some default situation. So here, for the number of codes that you can form with the 4 different elements, it's just similar to case 1. okay, when they tell you that they're different digits. It's similar to the rearrangement of 4 different elements. But what about when they tell you that the elements may be repeated? Well, it's actually this the situation, right? You set your 4 spaces and then you establish a number of options. Since you can repeat any symbol, then you can have the full number of options for each position. 4 times 4 times 4 times 4. That is 4 up to 4, right? Which is actually 256. That's it. Okay, so you have those 2 possibilities. And besides, you can have also individual restrictions for each space. For example, using the digits 0 to 9, find the number of 5-digit codes that can be created such that the first digit cannot be 0 and that reads the same from left to right as from right to left. So you can try a few codes first. 5-digit codes that read the same from left to right and from right to left. So this is the palindrome numbers, right? So here you have an example. Another could be this, right? Or it could be this. But it couldn't be something like this because 0 can be in the first position. So you know what kind of codes you can make up. And if you set the 5 spaces, right, for the 5 positions of the code, you can reason that the first one, since it cannot be 0, you can just have 9 options. Okay, you just drop in the option 0. Then for the second and the third, in all the codes here, you can see that you can freely choose any possibility. Since they don't mention anything about repetition, you assume that the elements may be repeated. So you have the full 10 choices in the third position as well. Now, what happens with the fourth position of this code? You have just one option, which is to copy the digit used in the second position, right? Because that's what makes the number readable from right to left, the same as from left to right. And in the fifth position, you can just copy the digit used in the first position. So you also have just one possibility. Okay, after you multiply all the other options, you get 900 possible codes with these characteristics. All right, let's consider the case number 3, subgroups. Let's say, for example, that they ask you to make a group of 3 elements, choosing from a total of 7 elements, the 7 letters from A to G. Okay, we could set, the 3 spaces and analyze the number of options. The first of these 3 letters, I could choose from the 7 elements, so any of them could be. After I've chosen one, then I can pick the next from the remaining 6, and so on. I have 5 to pick from in the third position. The product of this is 210. As you can see, it includes not only trios of 3 different letters, but also trios where the 3 same letters are arranged in some other way. Like, for example, here. So if you want to consider all the ways in which the same elements in the group can be arranged, you just do this calculation, okay? Do the methods of the 3 steps, and that's it. You're good to go. But there is some, situation in which you may need to do otherwise. For example, that is when they tell you that the number of subgroups of 3 elements that you're counting actually don't mind the different order, okay? So in this case, you don't want to count the same trios in different order. You just want to count trios that be different from one another in at least one element. So here you should have trios like this: ABC, EDF, CFG, etc. Okay, after you have calculated the number of different subgroups, including those same subgroups in a different order, you want to eliminate the number of repeated subgroups, such as in this case, these and these, etc. So since a trio of elements can rotate the positions in 3 factorial ways, that is 6 ways, then you divide by 3 factorial in order to remove those repetitions, and you get to the number of subgroups with that characteristic, 35. So if you want to consider only one arrangement for every group of elements, so you need to divide by the number of elements in the subgroup, the factorial of that number. Okay. Let's move on to an example. In how many ways can we select one president and one assistant from a group of 4 people? So if we have 4 people, such as A, B, C, and D, here we have a case in which the president and the assistant are 2 different people, right? So we want to actually calculate subgroups of 2. So we set up 2 spaces here. One could be the president's position, the other the assistant position. So you say, okay, I can pick the president out of 4 different persons. After I have chosen the president, I can pick the assistant in 3 different manners. So the total number of subgroups is 4 times 3 equals 12. Here, we do not divide by 2 factorial. Why? Because here, the different order of the same elements in the subgroup represent different roles within the subgroup. Okay? Like these 2 are not the same. So, in general, when making subgroups of people, we always divide, unless the problem differentiates the people by roles or position. For example, they may tell you that the subgroups for example, have a different order, meaning different position. Imagine that in this problem, they told you we have 7 racers running the 100 meters, run. In only 3 of them will go to the podium for a medal, right? Gold, silver, or bronze. So in how many ways could the 3 medals be awarded to 3 of the people from this group of 7? Actually, this would be the correct way of calculating. Because here, for example, ABC, okay, here you have gold, silver, and bronze. So this awarding of the medals would be different from this one, right? Totally different. So when there are roles or different positions within the subgroup, you don't divide. Let's move on to another example, which is also very typical in the GMAT. That is called the multiple subgroups problem. There are 4 women and 3 men from which a group of 4 people must be formed. In how many ways can we select 2 women and 2 men to form the group? So here, we're trying to form a subgroup of 4 people out of these 7 people here. But it's not just any 4 people. They must comply with a certain structure. 2 women of one group and 2 men of the other group. So first, we can calculate in how many ways we can select 2 women out of 4. So this is simple. You just set the 2 spaces. After setting up the 2 spaces, you just pick the number of options for each space. You have 4 times 3, and then divide by 2 factorial. Since, for example, Rosa and Luisa is the same as Luisa and Rosa, right? So you get 6 possible duos of women. What about the men? Picking up 2 men out of 3, you can do by this formula, 3 times 2 divided by 2 factorial, since Felipe and Carlos is the same as Carlos and Felipe. So you have 3 possible duos of men. So now you use, again, the multiplication principle. You want to combine a duo of women, right? And a duo of men. You want to combine 1 duo of women and 1 duo of men in order to assemble 4 people. So in how many ways can you assemble such a group? Well, you have 6 options for the duos of women, 3 options for the duos of men. 6 times 3 should be 18. Okay, so that's it. Okay, so when we do subgroups that come from different sources, we do it separately. And after we calculated the separate number of subgroups, we multiply at the end.